Surface integrals are used to calculate the surface area of objects in R3. For example, the surface area of a sphere, a paraboloid, planes, or other structures. Because this is a kind of applied topic, I don't want to talk too much about mathematical conditions, and more about what the surface integral actually is and how you can calculate it. So, first of all, we need a way to represent surfaces mathematically, or in other words, we need a parametrization of surfaces in R3. You may already know that you can parameterize functions in the real numbers the following way. So, you have a function f from the interval a, b to the real numbers r. Then the parametrization looks like that. It's a function phi from the interval a, b, which we call t, to r2, and phi of x is equal to x and f of x. Here you can see what is happening. This green curve is the image of phi and describes the function f. You need this parametrization, for example, if you want to find the length of this green curve here. Okay, now I will show you that you can parameterize surfaces in a similar way. So we have a map phi again, this time from a subset T of R2 to the space R3. The parametrization looks like that. Phi of x, y is equal to x, y, and z of x, y. By the way, we also call this parametrization as a graph. So here we have the coordinates x and y in the xy plane. And that here describes the height of the surface in each point x and y. Here I have a picture again. So this here is x, that here is y, and this here is z of xy. If we have a compact subset K of the set T, the image of K could look like that, phi of K. This green surface here. The goal is now to find the area of this green object here. So the goal is to find the area of phi k, of this image here. But first of all, let's take a look at some examples of surfaces. The first parametrization looks like that. So phi of xy is equal to x, y, and h is a real number. This is just a plane at constant height h. Nothing interesting at all. Here you have a picture of it. So this here describes a plane at constant height h. The second parametrization describes a paraboloid. So this here is the parametrization of a paraboloid. Phi of x, y is equal to x, y, and c minus x squared plus y squared, where c is a positive number. Here I have a picture of such a paraboloid. So the maximum is here at c, and this is a picture of such a paraboloid. Now we are ready to define surface integrals. Let T be an open subset of R2. Let phi be some surface parametrization, so a function from the subset T to the space R3 that looks like that here. dx phi denotes the derivative of phi with respect to x, and dy phi denotes the derivative of phi with respect to y. N phi xy is the normal vector that is orthogonal on dx phi and dy phi. So n phi xy is the cross product of dx phi and dy phi. This cross here denotes the cross product in R3. Let K be a compact subset of the set T, and let f be a continuous function from phi t to R. Then this here, the integral over K of f of phi of xy times the Euclidean norm of this normal vector here, n phi of xy dx dy, is called the surface integral of the function f over phi k. It is denoted like that. The S here stands for surface. If f is the function that is equal to 1 everywhere, then a of phi k, which is equal to the integral over k of the Euclidean norm of n phi xy, which is this normal vector here, dx dy, is called the surface area of phi k. The second part of the definition is more important for us, because it tells us how to calculate the surface area of parametrized surfaces phi k. The surface area is given by that integral here. The first part of the definition is the general definition of a surface integral. This is important for physics. For example, the function f could be a temperature or density function. But as I said before, we will focus on that here, because we want to find the surface area of objects in R3. First of all, I want to give some notes. You need to know how to calculate the cross product of vectors in R3, because you need the cross product for the calculation of the normal vector n phi xy. The cross product in R3 is not too difficult. So the result is a vector again. For the first entry of this cross product here, you need to ignore the first line here, and then you have to calculate the determinant of this submatrix here. So A2 times B3 minus A3 times B2. So this is the first entry of the cross product. For the second entry of the cross product, you have to ignore this line here, and then you have to calculate the determinant of the still visible submatrix. So A1 times B3 minus A3 times B1. In the end, you also need a minus sign here, so it's minus this determinant of the submatrix. Don't forget the minus sign. For the third entry of the cross product, you have to ignore this line here, the third line, and then you have to calculate the determinant of the still visible submatrix. So A1 times B2 minus A2 times B1. This is the third entry of the cross product vector. Secondly, you need to know which norm we are using in the definition here. It's the Euclidean norm for a vector in R3. So the Euclidean norm of a vector in R3 is equal to the square root of the first entry squared plus the second entry squared plus the third entry squared. So this here is the Euclidean norm of a vector in R3. Finally, I will try to explain to you why this integral here actually calculates the surface area of phi k. So let xy be some point in the set k. You also have the derivatives of the parametrization phi with respect to x and y, which you can see here in this picture. These derivatives are vectors in R3 again. You know that derivatives are a good way to approximate functions as long as you are near the point xy. So you multiply these derivatives with small numbers dx and dy. These two vectors could now look like this here. So here you have dx phi times dx, and here you have dy phi times dy. You see, these two vectors form a parallelogram. You're interested in the area of this small parallelogram. So you use the formula for the area of a parallelogram you may already know from school. The length of one side of the parallelogram times the length of the other side of the parallelogram times the sine of the angle between the two vectors, which we call phi here. We rewrite this a little bit and take a look at this here. You can write this by using the cross product in R3. You can show that this here is the norm of the cross product of the derivatives with respect to x and y. So this here is equal to that here. We also called this cross product the normal vector of phi. So in the end, the area of this extremely small parallelogram is given by the Euclidean norm of the normal vector times dx dy. The last thing we have to do is to summarize continuously over all these extremely small area elements. So that means you have to integrate. That should explain why the surface area is given by this integral here. So it's just a continuous sum over all these very small area elements. Let's take a look at an example now. Our surface is the plane at constant height 1. We have already seen that it has the following parametrization. Phi of xy is equal to x, y, and 1. The set K is the following rectangle. We want to find the surface area of phi k. So the first thing we have to do is to differentiate phi with respect to x and y. So this here is the derivative with respect to x, and that here is the derivative of phi with respect to y. So to explain this here, the derivative of x with respect to x is 1, the derivative of y with respect to x is 0, and the derivative of 1 with respect to x is 0. And now I will explain this here. The derivative of x with respect to y is 0, the derivative of y with respect to y is 1, and the derivative of 1 with respect to y is 0 again. So these here are the derivatives. The next step is to calculate the cross product of dx and dy. What we get then is the normal vector n phi. So the normal vector n phi is this cross product here. So we have to calculate the cross product of this vector and that vector, which we have done here. So to explain this result here, for the first entry of the cross product vector, we have to ignore the first line here, and then we have to calculate 0 times 0 minus 0 times 1, which is 0. For the second entry of the cross product vector, we have to ignore the second line here, and then we have to calculate 1 times 0 minus 0 times 0, and we also need a minus sign, but in this case this is just 0, so we get 0 here. And for the last entry here, we ignore the last line here, and then we have to calculate 1 times 1 minus 0 times 0, which is 1. This explains this result here. Now you have to calculate the norm of this normal vector here. The Euclidean norm of this normal vector n phi is just 1, because this is the length of this vector here. The length is 1. And now the surface integral is this here. So the area of phi k is the integral over k of the Euclidean norm of n phi xy dx dy. Now we insert that here at this position here and get the integral over k of 1 dx dy. By solving this, you get the result b minus a times d minus c, which is the area of the rectangle K. That makes sense, because the surface is a plane at height 1. The image of K is just the rectangle K again, but at height 1, which you can see here in this picture. Let's take a look at something more interesting: the surface area of a paraboloid. That paraboloid has the following parametrization: phi of x, y is equal to x, y, and 2 minus x squared plus y squared. The set k are these x, y, so that x squared plus y squared is smaller or equal to. K describes a disk with a radius that is equal to the square root of 2. We want to find the surface area of the image of K. Here I have a picture of that paraboloid. We want to find the surface area of this, let's call it head here, so the positive part of the paraboloid. And here you can also see the disk K. What you can also see in this picture here is that the paraboloid is a rotation surface. So when you rotate this orange curve here around Z, you get the paraboloid, which means the paraboloid is a rotation surface. So it makes sense to do a coordinate change to polar coordinates. That means we write x as r times the cosine of phi and y as r times the sine of phi. Now we have new variables r and phi. R describes a positive radius and phi an angle between 0 and 2 pi. By using these new coordinates, we also get a new parametrization. So we have to insert x and y here in the old parametrization and get a new parametrization that depends on r and phi. So when doing so, we get phi of r phi is equal to r times cosine of phi, r times sine of phi, and 2 minus that here, which is x squared plus y squared, but in the new coordinates. Now we know that this here always has to be 1, so the cosine squared plus the sine squared is always 1. So in the end we get this here as a new parametrization. So this new parametrization depends on r phi and is equal to r times the cosine of phi, r times the sine of phi, and 2 minus r squared. And as I said before, you get this new parametrization here by inserting x and y here in the old parametrization. The set k becomes easier too, because x squared plus y squared is smaller or equal to, so that here means when we insert for x this here and for y that here, that r squared times the cosine squared plus the sine squared has to be smaller or equal to, because this here is 1, so the cosine squared plus the sine squared, we get that r squared has to be smaller or equal to, and that means that r has to be smaller or equal the square root of 2. So the set k becomes the following. So the set k is equal to this r phi, so that r is between 0 and the square root of 2, and phi is between 0 and 2 pi. So this here is our new set k. So now we have this new parametrization and that new k. Now we have to differentiate this phi with respect to r and phi. So we have done this here and there. You can check this yourself. Then we have to find the normal vector. So we have to calculate the cross product of these two vectors, which we have done here. So for the first entry of the cross product vector, you have to ignore the first line, and then you have to calculate sine of phi times 0 minus 2 times r times cosine of phi, which is 2 times r squared times the cosine of phi. For the second entry of the cross product vector, you have to ignore the second line here, and then you have to calculate minus r times sine phi times minus 2 times r minus cosine of phi times 0, which is 2 times r squared times the sine of phi. And for the last entry, you have to ignore this line here, and then you have to calculate the cosine times r times the cosine minus r times sine, which is r in the end, because the cosine squared plus the sine squared is equal to 1. Now we have to calculate the norm of this normal vector here. So the Euclidean norm of this vector here is equal to the square root of the first entry squared plus the second entry squared plus the third entry squared. This is equal to that here, because the cosine squared plus the sine squared is equal to 1. So we get this here. Now we can rewrite this a little bit, and in the end we get that here. So the norm of the normal vector n phi is equal to r times the square root of 4 times r squared plus 1. To find the surface area, we have to solve this integral here. So the area of phi k is equal to the integral over k of the Euclidean norm of n phi dr d phi. Now we can insert this here there, and for k we have to insert this here and that here, and then we get the integral of phi from 0 to 2 pi, the integral of r from 0 to the square root of 2 of r times the square root of 4 times r squared plus 1 dr d phi, because this here doesn't depend on phi at all, we get 2 pi times the integral of r is equal to 0 to the square root of 2 of the square root of 4r squared plus 1 times r dr. We solve this integral by using the substitution rule. So we set u as 4r squared plus 1. Then du is equal to 8r dr. From that follows that r dr is equal to du divided by 8. So we get that 4r squared plus 1 is equal to u, and r dr is equal to du divided by 8. So now this here is equal to that here. So this here is equal to 2 pi divided by 8 times the integral of u is equal to 1 to 9 of the square root of u du. Now we can solve this here, and in the end we should get 13 pi divided by 3. So the surface area of this paraboloid is given by this number here. So the surface area of this paraboloid is 13 pi divided by 3. At the end of this video, I want to note something. I want to show you what happens when you do this change in variables, not in the beginning, but later on. So let's assume you continue to use that parametrization of a paraboloid here. Phi of x, y is equal to x, y, and 2 minus x squared plus y squared. And k looks like this here again. Now you have to calculate the derivatives of phi with respect to x and y, which we have done here and there. This here is the derivative of phi with respect to x, and that here is the derivative of phi with respect to y. Now you have to calculate the cross product of these two vectors. What you get then is the normal vector n phi. So you have to calculate the cross product of these two vectors, and that here is the result. So for the first entry of the cross product vector, you have to ignore the first line, and then you have to calculate 0 times minus 2y minus 1 times minus 2x, which is 2x. For the second entry, you have to ignore the second line here, and then you have to calculate 1 times minus 2y, which is minus 2y, and something, a multiplication with 0. So in the end, you get minus 2y, and you need a minus sign for the second entry, so you get 2y. And for the last entry, you have to ignore the last line. Then you have to calculate 1 times 1 minus 0 times 0, which is 1. So this here is the normal vector n phi. Now you need the norm of this vector here. So the norm of this vector is the square root of the first entry squared plus the second entry squared plus the third entry squared. So in the end, you get this here. So the square root of 4 times x squared plus y squared plus 1. So this here is the norm of the normal vector. To calculate the surface area of the paraboloid, you have to calculate this integral here. So the integral over k of the Euclidean norm of the normal vector n phi dx dy. So you can now insert this here, and k is described by that here. So in the end, you get the following integral. This integral here over the disk of radius square root of 2 of the square root of 4 times x squared plus y squared plus 1 dx dy. And now you want to substitute polar coordinates for x and y to solve this. So you write x as r times cosine of phi and y as r times sine of phi. And now you substitute for x and y that here. So when inserting this here there, you get the following integral. The integral of phi from 0 to 2 pi, the integral of r from 0 to the square root of 2 of the square root of 4 times r squared plus 1. This follows from this substitution here. But because you are changing variables inside of an integral, you have to use the transformation or substitution rule for integrals. That means that you have to multiply this result here, the square root of 4r squared plus 1, with a correction value. So when you write this here as a function f of r phi, then the substitution or transformation rule tells you that dx dy is equal to the absolute value of the determinant of the derivative of this function f here times dr d phi. And this determinant here is the correction value we were talking about. In the case of polar coordinates, this correction value is just r. So the correction value in the case of polar coordinates is r. Now we have to insert this here, r times dr d phi, at this position here. So in the end, we get the following integral. So this here r is our correction value, and we have to multiply this correction value with the square root here. And we have already solved this integral here a few minutes ago. So in the end, this here is equal to 13 pi divided by 3 again. What I want to tell you by this, if you do this change in variables in the beginning so that you get a new parametrization phi and a new set k, you don't have to think about substitution rules and correction values at all. But if you do that change in variables later on, which we have done here, so a change in variables inside of an integral, then you have to be careful to not forget this correction value here, in our case r. Otherwise, you will get wrong results. Okay, I hope this video was helpful, because it was a lot of work to create it. If you liked this video, please consider subscribing to my channel. This would really help and motivate me to keep creating videos.